Okay, so we can start. First of all, let me thank everybody here for joining for this actually colloquium of our physics and astronomy department. As usual, let me introduce the speaker today, Professor Kolb from the University of Chicago, who is now sitting there. A few words to introduce you. For me is really a great pleasure to introduce Professor Kolb. He's actually the Arthur Holly Compton Distinguished Professor at the Astronomy and Astrophysics at the University of Chicago, a member there of the Enrico Fermi Institute and also of the Kavli Institute for Cosmological Physics. He did his PhD at the University of Texas at Austin, and then he was a postdoc in the theoretical division at the Los Alamos National Laboratory. He was actually there an Oppenheimer Research Fellow. And then he was a postdoc at the California Institute of Technology, where actually he was then a member of the staff member of the theoretical astrophysics group. In 1983, he was a founding head of the theoretical astrophysics group at Fermilab, and then in 2004, actually, he was the founding director of the Particle Astrophysics Center, still in Fermilab. From 2006 to 2012, he served as a chair of the Department of Astronomy and Astrophysics in Chicago, where he actually also was the dean of the division of the physical sciences. And he also was the director of the Kavli Institute for Cosmological Physics from 2019 to 2021. Let me recall that Professor Kolb actually is a worldwide expert for astroparticle physics, cosmology of the early universe. Actually, he gave seminal contributions and he opened different lines of research. Just to mention a few about the origin of dark matter, phase transitions, actually testing new particles and forces beyond the standard model, and application in general of particle physics to cosmology. I definitely need also to mention a textbook that he wrote in collaboration with Professor Turner, The Early Universe, that most of us actually know, and that really actually helped many students over the years to be trained on this subject, including me actually. So also for the young students is an occasion to meet him in person and not just to be a name on the book. Let me also mention at least a few of the many awards and honors that actually he got. Many of them also testifying his intense teaching activity and dissemination activity. Professor Kolb is a fellow of the American Academy of Arts and Sciences and a fellow of the American Physical Society. In 2024, he was the recipient of the Julius Edgar Lilienfeld Prize of the American Physical Society. The 2003 Oersted Medal of the American Association of Physics Teachers for notable contributions to the teaching of physics. The 1993 Quantrill Prize for Teaching Excellence at the University of Chicago, and the 2009 Excellence in Teaching Award from the Graham School of the University of Chicago. He wrote a book, Blind Watchers of the Sky, actually which received the 1996 Eugene M. Award of the American Astronautical Society. And he was recognized by the 2010 Denny Heinemann Prize for Astrophysics, which actually is awarded by the American Astronomical Society and also by the American Institute of Physics. He also actually holds a doctor honoris causa from the University of Lyon in France. And he was the recipient of the Hans Jensen Prize of the University of Heidelberg. So we are definitely thrilled to have Professor Kolb here, and today actually will tell us about whether the standard model of cosmology is broken, breaking, or healthy. So I leave the stage to Professor Kolb. Thank you.
Thank you. Thank you for that very nice introduction, but it sounded a bit like a eulogy. Okay, so I'm going to talk about cosmology because I'm a cosmologist, and I realize there are students here, so I thought I'd start by defining cosmology. It's a branch of metaphysics. Did you know that? I don't like this definition. Maybe it's a branch of astronomy that deals with the origin, structure, and space-time relationships in the universe. So I'm a cosmologist. I study the origin, composition, large-scale structure, and evolution of the universe. I connect the quantum and the cosmos. That's what I really like to do, connecting the smallest things in nature with the largest things in nature. I work at the intersection of astronomy and physics. Some of you may not know that there really is an intersection of astronomy and physics. There is physically an intersection of astronomy and physics. Does anyone know where it is? Don't say Italy, that's too easy. Does anyone know where the intersection of astronomy and physics is? Someone said it? Right, it's in Rome. And there I am working at the intersection of astronomy and physics. So I'm going to talk about the statement that's often made is that there is a crisis in cosmology. So what is a crisis? I'll work with, it's an unstable or crucial time, a state of affairs in which a decisive change is impending, especially one with the distinct possibility of a highly undesirable outcome. So is there a crisis in cosmology? Now, I don't know how much press these statements get in Padova or in Italy, but in the US, there's been so many of them. So just about a year ago, in the New York Times, which is the sort of newspaper of record in the US, there was an op-ed piece by Adam Frank and a former postdoc of mine and good friend Marcelo Gleiser saying the story of our universe may be starting to unravel. That sounds rather serious. And just a quick browse through Google, you can find a lot of papers like The Crisis in Cosmology, Crisis in Cosmology, The New Crisis in Cosmology. This symbol is for the public broadcasting system in the US. Well, it goes on and on. Cosmology crisis, why is this happening? Neil deGrasse Tyson is a public spokesperson of science. He writes about the crisis in cosmology. My colleague Wendy Friedman says, is there a crisis in cosmology as a question? And it's often said that in physics, if the title of something is a question, the answer is no. Wendy does not believe there is a crisis. Michel Kaku is also a public spokesperson of science, and he writes, there is a crisis in cosmology since we're off by a factor of 10 to the power of 120. This is understanding dark energy, and I'll talk about that. So, you know, apparently it's not just in the US that there is a crisis in cosmology. Cosmic voids in the crisis in cosmology. What is wrong with the lambda CDM standard model? Cosmology in crisis. I could spend the rest of the 50 minutes just doing it. I will. So cosmology crisis reloaded, consensus or crisis. I like this statement by my friend Ethan Siegel. The crisis in cosmology is pure exaggeration. Crisis in cosmology. You get the idea? This is from Scientific American, how a dispute over a single number became a cosmological crisis. Crisis. Some scientists speak of a crisis in cosmology. They have good reason. Big think, that sounds important. This is by Paul Sutter. Why is there a crisis in cosmology? October 2021. By February 2022, about 6 months later, is there really a crisis in cosmology? I like this. The crisis in cosmology is pure exaggeration. This is my last one. Standard model of cosmology survives a telescope's surprising finds. This was about a year ago. It seems that every week I get a phone call from a journalist saying, what do you think about the crisis in cosmology? And often say, what crisis? And they hang up, which is good. Okay, now it's often stated that we are in the era of precision cosmology. But are we in the era of accurate cosmology? I'm not that impressed with precision. So this is an example of a target. This is a precision result. Look at that. All those holes are very clustered, but it's not accurate. I think it's better to be accurate than to be precise. So don't be fooled just because something says it's precise. All right, so what am I going to talk about is cosmology in crisis. Well, there is a standard cosmological model that goes by the name of lambda CDM. Lambda stands for Einstein's cosmological constant. Lambda and CDM for cold dark matter. So we have a standard model, but there are issues. So I'll discuss 4 of the issues today. The nature of dark matter, the nature of dark energy, the Hubble tension, and something that's known as the sigma 8 tension in understanding large-scale structure. I will not discuss violation of cosmological principle, small-scale structure issues, El Gordo. I guess that's Spanish. In Italian, it would be the fat one, the fat one. Galaxy cluster collision, big voids, lots of early bright galaxies, parity violation in endpoint statistics. Seems that every day that somebody comes up with a new crisis in cosmology. So in my opinion, the issues, these are issues, do not rise to the level of crises, but might one day soon. We cannot say we have an understanding of the present mass energy of the universe. We do not have a single theory of inflation, and personally, I would welcome a crisis, because in science, a crisis leads to opportunity. So let me start by talking about dark matter and dark energy. And as a cosmologist in our union, we are forced to show a slide like this in every lecture. This is the present composition of the universe in the standard cosmological model. So the early universe that I like to study was radiation dominated, but today most of the radiation in the universe in the microwave region, the cosmic microwave background radiation, consists only 0.005% of the mass and energy of the universe. This figure also explains why chemistry is not important. Chemistry, by which I define as chemical elements other than hydrogen and helium, is only 0.025% of what's in the universe. Why bother studying such a small part of the universe? Neutrinos, something that I started in cosmology studying, is a much larger part of the universe than the chemical elements. Stars that my friends in the astronomy department like to study is less than 1%. Most of the normal matter in the universe, hydrogen and helium, is in a hot gas that's to be found in clusters of galaxies. and it consists of roughly 4% of what's in the universe. So if you add up everything that we sort of study and know about that's in the universe, it's only about 5%. We understand 5% of the universe. To me, that's sort of a crisis, but it's also an opportunity. 25% of the present mass energy in the universe is in dark matter that I'll talk about, but 70% is in the form of something that we call dark energy. First, dark matter. There is the evidence for dark matter comes on many scales and has been around at least since the 1930s. Evidence for dark matter comes from cluster dynamics, galactic rotation curves, looking at the mass to light ratio of dwarf galaxies, from gravitational lensing, from Big Bang nucleosynthesis, looking at the cluster gas in X-rays, the cosmic background radiation, structure formation, cluster collisions. I could go on. The evidence for dark matter that there's more to the mass in the universe than we can account for is overwhelming. So it's a strange thing that if we look at a galaxy, most people would recognize this as a galaxy, we're not seeing the dark matter. We're only seeing a small fraction of what's there. And if we would look at what a galaxy really consists of, it would be the visible part of the galaxy here in the center, but surrounded by a halo of dark matter shown in red, whatever color that is, blue. And it's much larger. Dark matter extends much larger than the visible part of the galaxy. And the simulations say that there should be halos of dark matter around in the galaxy. So we're only seeing, when we look at an image of a galaxy, it's beautiful. I think it's beautiful. We're only seeing a small part of the galaxy. So most of the matter in the universe is dark, and it's not even normal stuff. It's not the kind of stuff that you would find on pizza toppings. You know, it's some other kind of matter. It's not the chemical elements. So the big question is, what is the nature of dark matter? And this is an image from the James Webb Space Telescope. And the universe is sort of asking, what is the nature of dark matter? So there are missing pieces in our picture of a galaxy. So what could this dark matter be? Well, I'll talk about a couple of ideas. One is that, well, there's not really dark matter. We only infer the existence of dark matter because Einstein or Newton didn't have the last word. And this goes by modified gravity. Maybe gravity is modified on large distance scales. Or some people have said that there's modified Newtonian dynamics. For instance, force is not equal to mass times acceleration. So if there are any students here, you don't have to assume force is equal to mass times acceleration, but you may want to use that in your test. But is there any evidence that force is not equal to mass times acceleration? I found some. Velocity is equal to mass times acceleration. That is non-Newtonian dynamics. And you have to take this seriously. This is a Swiss precision instrument. It's a chronometer. It's not even a watch. The difference is about 5,000 Swiss francs, as you know. So anyway, that's the only evidence I could find for modified Newtonian dynamics. So I don't think that's the right answer. Then people have proposed the possibility that the dark matter is really normal matter, but it's in the form that's not shining at us. And some possibilities people have proposed is that it's rocky rogue planets. It's rocky planets, my favorite type of planet, rocky planets that are not associated with stars but free-floating in the galaxy. It could be mass-challenged stars, stars that are smaller than about 6% of the mass of the sun, would be very difficult to see, or black holes. These go by the name of massive compact halo objects, or MACHOs. It's very difficult, in my opinion, to have a MACHO that have escaped all of the limits we can put on such characters. So the most popular idea for dark matter, in other words, something that I work on, is that it is an unknown dark matter particle species, and it's known as a WIMP, a weakly interacting massive particle. So it seems that WIMPs are more important than MACHOs. Who would have thought that would be true? So it's a particle dark matter candidates. I need more than 2 colloquia to talk about, just to list all of the particle dark matter candidates. I'll just run through some broad classifications. Sub-eV mass neutrinos. So we're pretty sure that WIMPs exist. Neutrinos are weakly interacting massive particles, and they're hot dark matter. So WIMPs do exist, but sub-eV mass neutrinos are not massive enough to be the dark matter. Then people talk about stereoneutrinos or gravitini, the lightest supersymmetric particle, the lightest Kaluza-Klein particle, Bose-Einstein condensates, axions, axion mini-clusters, solitons, Q-balls, B-balls, supermassive WIMPzillas, and I've actually worked on many of these. But the work of theorists over 60 years, you have to appreciate that's hard work, has gone into limiting the mass of the dark matter particle and its interaction strength. So 60 years of hard theoretical work has limited the mass of the particle to 50, 70, 81 orders of magnitude in mass. That's a pretty good limit. That's a pretty tight limit, isn't it? And for the interaction strength, it could have only gravitational interactions, WIMPzillas, or it could be strongly interacting, known as B-balls. So let me follow up this idea that dark matter is a WIMP. So here's the story. The story is, don't look now, but invisible things are passing through you. A mysterious, invisible particle species is all around us, a relic of the first fraction of a second of the universe, and there's about 10 to the 7 in this room at any instant, flying around at about 1 million kilometers per hour, and about 10 to the 12 of them will pass through you during this talk. But you can't see them, you can't feel them, you can't smell them, and yet they shape the large-scale structure of the universe. Now, try sitting next to a person on the train that you don't know and tell them this story. They are sure to get up and find another seat because they think you might be a little bit crazy. All right, so 95% of the dark energy, of the mass energy in the universe is dark, 25% dark matter, 70% dark energy. Dark matter is usually assumed to be non-baryonic, not quark nuggets, not 30 solar mass black holes, planets, dim little stars, cold today, slowly moving, dissipationless, doesn't dissipate energy, not self-interacting, it's associated with all galaxies and other structures, and it's a particle that's stable with a lifetime larger than the age of the universe, no strong and electromagnetic interactions. So just assuming those properties for the dark matter seems to explain all of the astronomical observations. But is that enough? So since I'm here in Padua, I thought I would do a little Galileo invitation. And imagine we have a debate between Simplicio and Salviati. Now, Simplicio would say, I don't care about the nature of dark matter. As long as it's dark, cold, and dissipationless, cold, dark matter, I can calculate, simulate its role in the evolution of structure and understand necessary astrophysics. So in some sense, an astrophysicist, if you're only interested in explaining what's around you, you don't have to know anything about dark matter other than it's cold and dissipationless. Now, Salviati would say, I care about the nature of dark matter because it must exist for a reason other than to be a part of Simplicio's code. Feynman said, nature weaves its tapestry from the largest threads. What is the dark matter thread? So I want to know what is the nature of dark matter, not just that it exists in cold and dissipationless. How does it fit into some larger picture of nature? So again, I talked about the dark matter particle mass range going between 10 to the minus 22 electron volts to 10 to the 19 GeV, the Planck scale. So we think the mass would have to be larger than 10 to the minus 22 electron volts, because if it was lighter than that, the de Broglie wavelength of the particle would be larger than dark matter dominated objects. Sorry, that should be larger. And we think it has to be smaller than the Planck mass for it to be a particle. And if it's a fermion, it has to be larger than a few electron volts in order to evade the Pauli exclusion principle and pack enough of them in galaxies. If it's the result of thermal freeze-out, the mass has to be larger than the electron mass because it would have to annihilate the standard model particles. And the mass has to be smaller than about 100 TeV. Otherwise, the annihilation cross-section would be too small for larger masses. So is dark matter a particle or a wave? If the mass is smaller than an electron volt, the occupation number in a de Broglie wavelength volume would be larger than 1, and that would be a wave. If the mass is larger than the electron volt, the occupation number would be smaller than 1, and we can talk about it as a particle. These are some of the proposals for the dark matter particle. It could be a plankton, which has a mass of the Planck mass. Now, there are little things swimming around in the ocean that has a Planck mass. Planktons have a Planck mass. So maybe the dark matter particle is a plankton, not swimming around in the ocean, but has a Planck mass. WIMPs that I've been working on would have a mass comparable to the mass of the inflaton, maybe in this mass range, and it's supermassive dark matter would have a mass larger than 100 TeV. The WIMP range, for instance, a neutralino, would have a mass larger than a proton mass, smaller than a TeV. Then people talk about light dark matter, for instance, a dark photon, which would have a mass larger than an electron mass and smaller than a proton mass. Ultralight dark matter, for instance, an axion, a mass smaller than 1 electron volt. And fuzzy dark matter would have a mass of about 10 to the minus 22 electron volts. So the most popular paradigm for dark matter is a cold thermal relic. And what is a relic? It's an object of particular veneration, according to the dictionary, and we venerate dark matter relics. The dark matter abundance would be set by creation or annihilation with standard model particles. Equilibrium abundance of the dark matter is determined by the ratio of the mass over the temperature, assuming there's no asymmetry. The dark matter species' final abundance is determined by freeze out of equilibrium or freeze in to final abundance. So you can imagine the dark matter species starts in equilibrium, but then freezes out of equilibrium to give the correct abundance, or maybe it starts with 0 number density and slowly built up and freezes in to the proper value. And the freeze out, freeze in interplay is an interplay between particle physics, the dark matter standard model interactions, and the expansion rate of the universe, gravity. Now, the great thing about a cold thermal relic has a dark matter interacting with the standard model, so it should be able to be discovered. And it could be discovered 3 ways. One is direct detection, where a relic dark matter has a rare scattering with a target, and the issues include background and detection. So you have some target deep underground or in a tunnel, like Gran Sasso, and the relic WIMP comes in and occasionally just bumps a nucleus that you detect somehow. Or there's something known as indirect detection, where the relic dark matter in, for instance, galactic center annihilates and produces detectable radiation. The issue here is astronomical foregrounds. So dark matter annihilates, producing quarks, high-energy quarks, leptons, and bosons, which produce protons, antiprotons, neutrinos, electrons, positrons, and somehow you have to dig this signal out from what the expected background is. Or if the WIMP was produced in the primordial soup, then if you reproduce the primordial soup on Earth, for instance, in collisions at CERN, at the LHC, in an accelerator, then you should be able to produce dark matter. So there were 3 methods, 3 ways to detect dark matter. And I used to give colloquia saying the 2010s will be the decade of the WIMP. It will be so exciting. We will see WIMPs underground in direct detection. We will see evidence of WIMPs from indirect detection. We will see, bound to see something new with the LHC. And it will be a great decade trying to piece these things together to figure out what the WIMP is. Now, unfortunately, none of those things have been seen. For instance, this is an exclusion plot for direct detection based upon nuclear recoil. This is the spin-independent dark matter nucleon cross-section plotted here, and the mass of the WIMP plotted here. And there is this blue area. That's the neutrino fog. That would be something that could be a signal that could be produced by background neutrinos. And these are the various experiments that are pushing down to the neutrino floor. And it's remarkable to me, when I first started working in this, we were talking about picobarn cross-sections. Now we're at the zeptobarn limit for the cross-section, and it continues to go down. There's a similar exclusion plot for axion-like particles. Axions have not been discovered, but experiments are pushing down into the expected range here in yellow for the QCD axion. And, okay, well, there's news this week. I hope this means breaking news or something, and it's, you know, I know just enough Italian to say something really stupid and offensive, so, okay, so it's okay to say this? All right, good. Just yesterday, Paolo Privatera, my colleague next door to my office in Chicago, reported from the Modane Underground Laboratory. This is an experiment, rather than using nuclear recoil to try to discover WIMPs, it uses CCDs. And he's able to I don't know what the hell this means, actually, but it's something that he can use to avoid backgrounds. And he's placing limits. The dark line here is his experiment Damic M, Modan, I guess. And this is the prediction from freeze in, predictions from freeze out. And you see they're going down excluding ranges where one might expect to have a WIMP, a light WIMP. All right, so where's the WIMP? No signal in direct, indirect, or accelerator searches. Even more troubling to me is no sign of beyond the standard model physics at the LHC. So this doesn't seem to be the decade of the WIMP. Perhaps dark matter is not a WIMP, not a cold thermal relic, so perhaps it's time to focus elsewhere. Maybe go lighter. People are working about things in the dark sector. Go ultralight, axion, or a dark photon. Go ultra heavy, a WIMPzilla, or boldly go where no one has gone before. This is sort of a mashup of various models done by my friend and colleague Tim Tate. And you know, there are a lot of possibilities, and I've worked on many of the, wasted time working on many of these. You know, there are many theories of dark matter. So is dark matter really a WIMP? Well, observation and experiment will tell. So far, after 30 years of effort, nothing definite seen. So do we keep looking or pursue other ideas? And what we hope for is a disruptive discovery. We need a disruption in this field. Will it come from a kilometer underground? Some dark matter experiment in a tunnel or underground. Will it come from 100 meters underground, say at the LHC? Will it come from 2,400 meters above ground, some telescope observation? Or will it come from 1,000,000 kilometers above ground, say an experiment at L2? So what sort of disruptive particle discovery might there be? Well, you might produce something at the LHC, who knows? Anything new at the LHC. Could discover an axion in some of these experiments, could see a dark sector in fixed target experiments, discover a dark photon, see dark matter underground. So there is a result looking at G-2 of the muon that's not in line with standard model prediction. And some people have doubted this, whether we really know, are really able to calculate the standard model G-2 of the muon to sufficient accuracy. Or will we discover an unexpected neutrino mass? There could also be disruptive astro observations. LIGO Virgo could discover black holes less than the Chandrasekhar mass, say less than 1 solar mass. This would really point to primordial black holes. Perhaps primordial black holes could be dark matter. Could be observations from high redshifts, a larger than 10 universe, and the assembly of galaxies can't be described by lambda CDM. A gamma ray excess in many systems. Perhaps we see a gamma ray excess from the galactic center, but do we see it in dwarf spheroidals, the Large Magellanic Cloud, M31, and proportional to what we expect it to be proportional to if it's dark matter? Perhaps there, I don't think so, an unexplained universal 3.5 keV line. And anything that can't be explained by CDM, cold dark matter simulations. A lot of effort goes into simulating structure in cold dark matter. Now you might ask, what is a simulation? Well, there's an official French dictionary. I don't think there's an official Italian dictionary. There's no official English dictionary, but the dictionary of choice is the Oxford English Dictionary. What is a simulation? It is the action or practice of simulating with intent to deceive, a false pretense, and a deceitful profession. So if you're a student and your advisor says, I would like you to do a simulation, you know exactly what's being asked of you. And what could not be described by the cold dark matter simulation? Self-interactions of warm components, small-scale structure, mini-clusters, lensing, minimum halo mass, core cusp, high redshift galaxies. So the good news is there are a lot of new observatories coming online. LSST, James Webb is up there. Extremely large telescopes are being built. Euclid satellite, the Roman satellite. We will be interrogating nature in ways that we haven't before, and perhaps something will turn up. Or I'll talk about a failure of lambda CDM. There could be an H0 tension or hypertension or a tension in something that I'll define as sigma 8. So that's all I want to say about dark matter for a moment. But there's more to the dark side than just dark matter. There's dark energy. Here's another story you may tell someone sitting next to you on a train if you want them to move away from you. Tell them Hubble's law measures the expansion velocity of the universe today, but farther out in space, as we look farther out in space, we look further back in time, and we use these using supernovae as standard candles. So we can measure the expansion velocity at early time. What's the difference in velocity? It's acceleration. Gravity is attractive, we think. So we expect the expansion of the universe to decelerate because of the gravitational force of all the matter in the universe. But there's a surprise that in 1998, astronomers measured acceleration rather than deceleration. We don't understand this, but the simplest explanation is that today in the universe there is a cosmological constant as proposed by Einstein in 1917. So here's a story. In 1917, Einstein proposed the cosmological constant in order to have a static universe. In 1929, Hubble discovered that the universe isn't static, but the universe is expanding. And Einstein in 1934 abandoned the cosmological constant. He called it his biggest blunder. He didn't appreciate that 64 years later, astronomers would find evidence for the cosmological constant. So here's the lesson. Never admit you're wrong. Einstein could have been famous, but he abandoned the cosmological constant and has faded into obscurity. So here's the strange thing about the cosmological constant. I describe it as the unbearable lightness of nothing. The cosmological constant is equivalent to a mass density of completely empty space, of nothing. I challenge my students to think about nothing. Some of them are really good. I say, close your eyes and think about nothing. Boy, they're on it immediately. But imagine nothing, no matter and no radiation. Nothing seems to have a mass density of about 10 to the minus 30 grams per cubic centimeter. It's really small, but it's not zero. And rather than the cosmological constant, I'd like to think of it as the cosmo-illogical constant. The magnitude of it doesn't make sense. It's so small and not zero. There is no symmetry that would enforce lambda equal to 0. And in physics, if we encounter a small number, in the limit that that small number goes to 0, we expect to uncover a symmetry. The dark energy corresponds to an energy density of 2 times 10 to the minus 3 electron volts to the 4th power, What is that related to? Well, people point out that it's maybe neutrino mass to the 4th power, but getting that to work hasn't been easy. So nothing is mysterious. It's an illogical magnitude. What is it related to? Again, the observed dark energy density is 10 to the minus 30 grams per cubic centimeter. I can calculate the energy due to quantum uncertainty. Doing a completely honest calculation, it's infinity to the 4th power. That's not a good answer. Then I say, well, I can cut it off at the Planck scale. I get 10 to the 90 grams per cubic centimeter. Again, 120 orders of magnitude wrong. Then I work really hard, push things really hard with supersymmetry. I can get 10 to the 30 grams per cubic centimeter, and except for a strange sign, so it's only off 60 orders of magnitude, then there's symmetry breaking in grand unified theories, electroweak theories, SUSY, chirosymmetries, etc. Everything is so large. And my friends who are string theorists, actually I don't have any friends who are string theorists. But if I did, they would tell me that there are extra dimensions that are wound up very tight. That's something else to tell a person on the train. There's 6 other dimensions, but they're really small and you can't see them. They'll move away from you. That would give maybe 10 to the 90 grams per cubic centimeter. So what's going on? So there's a way to take sides. We can't hide from the data. Lambda CDM is too good. And supernovae, subtraction, baryon acoustic oscillation, galaxy clusters, weak lensing, all point to the existence of a cosmological constant, or more appropriately, the expansion rate as a function of redshift is not given by Einstein de Sitter. So if we look at the Einstein equations, G00 from using the Robertson-Walker metric is not equal to 8 pi G T00 just with matter. So we could modify the right-hand side of the Einstein equations. Maybe it's a cosmological constant, just a cosmo-illogical constant, or maybe it's not constant, dynamics driven by a scalar field, or we can modify the left-hand side of the Einstein equations. None GR, branes, F of R, et cetera. There are many theories for do this, or it's just Einstein back reaction of inhomogeneity, something I worked on with Sabino that doesn't work, but it's still a great idea. It was Sabino's idea. That's why it didn't work. So that's modifying the right-hand side. What about the left? That's modifying the left-hand side. What about modifying the right-hand side? What theoretical tools do we have to modify the right-hand side of the Einstein equation? Well, you might say, I'm a theorist. What do I know about tools? Well, I owned 2 cars in my life that gave me great experience with tools. When I was an undergraduate, I had this marvel of British engineering, a 1964 Austin Healey Sprite. If you ever owned a British sports car, you know you use a lot of tools. Every weekend I was under the hood. So when I went to graduate school, I graduated from a marvel of British engineering to a marvel of Italian engineering. And I had a Fiat 128. Again, I used a lot of tools. Every weekend I had to be fixing it. So what did I learn about tools? There are only 2 indispensable tools: duct tape and WD-40. Here's how you use them. Do you want something to move? No. Does it? No. No problem. If it doesn't move, if it moves and you don't want it to, you use duct tape. And the rule is, if duct tape hasn't fixed the problem, you haven't used enough duct tape. Or maybe you want it to move and it doesn't. Well, if you want it to move and it does, there's no problem. If it doesn't, WD-40, is that known in Italy? So anyway, those are the only 2 indispensable tools. And the physics equivalent to duct tape is known as the anthropic principle that I will talk about. And the theoretical equivalent of WD-40 is known as quintessence. So here's something about the vacuum energy. During inflation in the early universe, there was a dark energy that dominates, and the scale factor grew exponentially. Then there was some transition where inflation ends, and the dark energy was converted to radiation and matter. We made primordial soup, and the first radiation dominates, then matter dominates. But if there is a cosmological constant, then today it's not quite at zero potential energy. There's some vacuum energy, and it's inflation again. Again, dark energy dominates. A of t will eventually grow exponentially, but the energy density of the vacuum is perhaps 10 to the 100 times smaller than what it was during inflation. So this is where we use duct tape in the anthropic principle or faith-based reasoning. There are many sources of vacuum energy. String theory, if I had friends who were string theorists, they would tell me that there's many, perhaps larger than 10 to the 500 possible vacua with different cosmological constants. Some of them corresponds to conditions. Some of them correspond to cancellations that yield a very small lambda. Although those exponentially uncommon, they are preferred because more common values of lambda results in an inhospitable universe. That's the duct tape solution. But if there is a cosmological constant, in the future the universe will approach a de Sitter solution. De Sitter solutions are notoriously difficult to obtain in string compactifications. And some of my friends here, they're not my friends, proposed de Sitter space is in something known as the swampland. The de Sitter swampland conjecture proposes that stable or metastable de Sitter space, a universe undergoing accelerated expansion, is not possible in a consistent theory of quantum gravity. Hence, de Sitter solutions are in something they called a swampland. So de Sitter is not consistent with quantum gravity, according to these people. The swampland. Now, I grew up in the swamp. I'm from Louisiana. I grew up in the swamp, and a swamp can be beautiful. You know, it's a beautiful thing. And teeming with life. Unfortunately, the life will sting, bite, or eat you, but it's teeming with life. So that's the duct tape anthropic solution. Then there's a quintessence solution that there are many possible contributions to the dark energy. Why is the total so small? Perhaps there's some unknown dynamics that we don't yet understand that sets the global vacuum energy equal to zero, but we're not there yet. That the vacuum energy, the cosmological constants, is slowly evolving in time, and this requires the mass of this mysterious field to be about the Hubble scale today, about 10 to the minus 33 electron volts. So modifying the left-hand side, there are various, I'm running out of time, so I just won't go through these. There are several possibilities. But this week, breaking news from the Dark Energy Spectroscopic Instrument that reported today, that they confirmed some earlier hints that the dark energy is not constant. And for a constant cosmological constant, the equation of state W, pressure over the energy density, is -1. If lambda changes in time, we can parameterize this by the value today plus something that describes how it changes with scale factor A. In lambda CDM, W0 is -1 and WA is 0. And the DESI results show that this solution is disfavored at 4.2 sigma. So this would be WA equal to 0, W0 equal to -1. There is the cosmological constant. And according to the latest DAISY results that were just announced today, dark energy seems to be evolving. So perhaps it's WD-40. Perhaps the dark energy is changing. All right, dark matter, dark energy. Reminds me of perhaps epicycles. Now, there was Alphonse the Wise, who had his astronomers construct Alphonsine tables for the Ptolemaic model. Ptolemaic model was about 135 CE. And in about the 12th century, the 13th century, Alphonse the Wise asked his astronomers to describe the universe, and they came up with this model. And it said that Alphonse the Wise looked over their shoulders and said, if I had been present at creation, I would have suggested a simpler scheme. Alphonse the Wise. I might say, if I had been present at creation, I would have suggested a simpler scheme. All right, so that's the story about dark matter and dark energy. Now let me talk about something that's known as the Hubble tension. Is the expansion rate of the universe the most fundamental thing in cosmology described by the standard cosmology? I think there's nothing more fundamental in cosmology than the expansion rate of the universe. It changes with time. Its evolution is given by the Friedmann equation in standard cosmology. The present value of the expansion rate is the Hubble constant, h0. There are two methods to determine h0, direct local measurements of h0 and infer h0 from the cosmic microwave background. The methods may not agree, and this is known as the Hubble tension. So determining the Hubble constant from local measurements, the traditional method is from the Hubble diagram. It's a magnitude redshift diagram. If we have a standard candle, magnitude is a proxy for distance, so it's a distance redshift relation. Historical standardizable candle is Cepheid variable stars, standardizable by Henrietta Leavitt's law. Now it's supplemented by type 1 supernovae, tip of the red giant branch stars, asymptotic giant branch stars, gravitational waves, gravitational lensing, water masers, etc. For all of these techniques, there are many systematic errors. Astronomy is really hard. We can also deduce the present value of the Hubble constant from CMB anisotropies. This is a map from Planck in 2018. It's fit with 6 cosmological parameters listed here: baryon density, cold dark matter density, etc. And it's remarkable that with 6 parameters, we get such a great fit to the angular power of the fluctuations. So we can determine h0 from CMB. The 6 parameters are determined from CMB measurements. The Hubble constant is not directly determined from CMB measurements, but can be derived from the 6 parameters, and using the standard cosmological model to evolve the expansion rate from CMB to the present time using the Friedmann equation, but this assumes the standard cosmology. So the Hubble tension is that the determination of h0 from local measurements do not match the determination of h0 from the CMB. My colleague Wendy Friedman describes it this way, that the 2 measurements do not agree. So I've slightly adopted Wendy's version. And so Adam Rees, this is Adam, that's Adam Rees, says that the local determination of h0 is 73.04, and the Planck satellite, which is sort of like God, so that's George Eustachian, right? Determines H naught is 67.4. It's a 5 sigma tension, so there's a big difference, according to Adam, between the local determination of H naught and the CMB determination of H naught. Again, this week has been pretty remarkable. There's new results from the Chicago Carnegie Hubble project that uses JWST and HST, and their determination of the Hubble constant is, so this is the Planck result, this is the DESI result, and this is the Chicago Carnegie Hubble project using tip of the red giant branch stars, 70.4 with a pretty significant error. So, you know, there's not much of a difference there because this is a large error bar. So using HST plus JWST plus supernovae and only the tip of the red giant branch, this is the Friedman et al. Result. And if you use only JWST, which Wendy thinks is the right way to go for the tip of the red giant branch and J asymptotic giant branch stars, you get a smaller number. And the conclusion of this paper, version 2, which appeared Monday, is our results are consistent with the current standard lambda CDM model without the need for the inclusion of new physics. So if you take Wendy's result, they don't quite touch, but they're pretty close, within a sigma or so. So if there is a Hubble tension, the statement is that you need new physics to resolve the Hubble tension. Di Valentino et al. In 2021 developed a rough classification scheme for proposed new physics and listed more than 1,000 papers that purport to explain the Hubble tension. A couple of years later, Ping and Wang listed the paper in 11 major categories with 123 subcategories for explaining the Hubble tension. The most popular explanation is to change the sound horizon at decoupling by changing the expansion rate at decoupling, and this is usually accomplished by something known as early dark energy, and there's one new paper per week on the archives talking about early dark energy, or to add extra relativistic degrees of freedom around recombination. Changing the sound horizon changes the best fit cosmological parameters. Maybe can work. Here's some of the papers, some of the techniques. But the solution is elusive. This is quoting from Di Valentino et al. Despite valiant ongoing efforts, no convincing explanation for the Hubble tension has yet been found. Some models can achieve H naught of 70 or 71, but reaching 73 or 74 has proven to be extremely difficult to obtain. A common problem is that ameliorating the Hubble tension comes at the expense of increasing the error bars, as well as worsening the sigma 8 tension. My take, for what it's worth, is never believe any observation until confirmed by theory, and this has not been confirmed by theory. But wait, breaking news today from the Atacama Cosmology telescope. It was a buzzkill. Data release 6 from the Atacama Cosmology telescope that appeared today in the archives claim we find no evidence for new light relativistic species. We also find no evidence for self-interacting dark radiation. We find H naught in this value consistent with CMB. And before this, there was a mild hint of early dark energy. Now, the mild hint of early dark energy in data release 4 was largely driven by a fluctuation, and the analysis of the new spectra is a high precision test, as to whether these features were the first hints of a real signal or simply a statistical fluctuation. Buzzkill, it was a statistical fluctuation. In general, models introduced to increase the Hubble constant or to decrease the amplitude of density fluctuations inferred by the primary CMB are not favored over lambda CDM by our data. Right, so the latest result is that there's no viable mechanism to explain the Hubble tension, if indeed there is a Hubble tension. I won't talk about the sigma 8 tension because I'm out of time. Just let me wind up. This is what I showed in the beginning. I don't think the issues rise to the level of crises, but might one day soon. I would welcome a crisis because it would lead to an opportunity. So what should particle physicists and astronomers do? Keep calm and carry on. Develop new ideas for dark matter, discover something new, anything new at the LHC. Understand lambda, or at least dark energy. Is it really a cosmological constant? Better accuracy in determining H0, better understanding of the high redshift universe, measure primordial gravitational waves in the CMB, measure non-Gaussianities in the CMB, understand the sigma 8 tension. So, is the standard model of cosmology broken, breaking, or healthy? Damn it, I think it's healthy. I would love to see a crack in the standard model, but I don't see it yet. Thank you.
Okay, thanks a lot for this great colloquium and questions. Don't be shy, especially the students.
Hello, my name is Olivia. I was wondering, when you were referring to the dark sector in fixed target experiments, what exactly would be a dark sector? Would it be experimental results which would indicate a gravitational interacting?
Yeah, so usually the dark sector is considered to be, so it could be that the dark matter is just out there, unrelated to anything else. But usually when you find one particle, you find many, right? So the dark sector might be there are other particles and interactions that talk amongst themselves, but not with the interactions in particles in the standard model. So there's a complete dark sector, all new physics, all new particles, all new forces out there that we don't see because it does not interact, maybe only gravitationally, with the particles and forces of the standard model. You really have to swallow a lot, but maybe that's true.
Thank you.
Other questions?
Ugo Gasparini speaking. Thanks for the nice talk. I am a particle physicist, so I am not very familiar with all this stuff that you explained us. I recently...
Don't apologize for being a particle physicist.
Okay. Recently I heard about news about the fact that there is a recent observation that the galaxies, the population of galaxies rotating, I don't remember now if counterclockwise from other or clockwise, are really different. Does this observation give some information about cosmology or not?
So this goes to a deeper question of whether there is a parity violation in cosmology. And one of the ways that this has been claimed to be there is calculating the three-point correlation function of galaxies in large-scale structure, in maps of galaxies. And there is a claim that I didn't talk about, as one of the issues that I didn't talk about, is that there is a parity violation. And where would a parity violation originate from? Well, people talk about, they say the magic word of Chern-Simons gravity or something like that, or a dark sector or something like that. So that doesn't, to me, it doesn't rise to the point where I would spend my time working on it. It doesn't mean well, I guess it does mean I think it's wrong, because if I thought it was right, I would work on it, but I have other things to work on.
Thank you very much for the talk. So personally, I see many things that could constitute a crisis, but I want to ask you, what would it take for you to say that cosmology or this model or everything is in crisis?
What would it take for me to think that there really is a crisis? I would point to the Hubble tension as number one. If I was really convinced that the local measurement of the expansion rate of the Hubble constant is known so accurately as to be in obvious disagreement, say at 5 or 6 sigma with the CMB, taking into account any systematic errors, then I would think that's a crisis that we don't understand the expansion rate of the universe. So I would point to that as the number one possibility of a crisis. And I guess the community agrees with that, because there's been over 1,000 papers trying to explain it. And if there's 1,000 explanations, that means there's not one good explanation. So that, to me, that would be the biggest crack.
Okay. Thank you for your speech. And the cosmology today, we know, is based on general relativity. And we also know that general relativity is a low energy theory of gravity. And we know that there should be a high energy, deeper theory of gravity underlying all the physics that we see today. And my question is, can dark matter and dark energy be the main characters of this new, deeper theory of gravity that we still don't know today, and we could not explain with general relativity, that is a low energy effective theory, but with this high energy, we could maybe explain this, and maybe the dark energy and dark matter will be the main characters. So I would like to ask, what do we know with the research today in this direction? And yes, the links between these two fields, and how are we proceeding in this direction with the research? Thank you.
Good question. The foundations of cosmology are general relativity and the standard model of particle physics. General relativity has passed every experimental test, but I don't think anyone truly thinks that it's the ultimate answer. Most people think it's the ultimate, where it breaks down would be at high energies, and many of these cosmological issues today come at very low energies, so it's hard to see how a breakdown in GR happens on scales of galaxies or clusters of galaxies or scales of the universe. But perhaps it's pointing to the fact that we don't have the final word on gravity. Also, or it's pointing to the fact that we don't have the final model of particle physics. And we have a standard model, but I don't think anyone thinks the standard model will be the ultimate description of nature. So that's one of the, correct, you point out that this is one of the reasons that physicists are so interested in cosmology, is perhaps these would be the threads, dark matter, dark energy, or something, would be the thread that you can pull on and watch the fabric of general relativity and the standard model of particle physics unravel. Wouldn't that be wonderful? That's the hope.
Thank you.
Thank you very much for attending.
Okay. Other questions? Okay, there's one.
Thank you very much for your talk. Can you comment more on the back reactions, which you wrote twice in the slides, but you didn't spend much time on?
Well, the idea of back reactions was this idea that, in fact, we model the expansion and evolution of the universe is inhomogeneous. We model the evolution of an inhomogeneous universe by that of a homogeneous universe with the average density of the inhomogeneous universe. Now, because GR is nonlinear, this cannot be correct to all orders. So there should be some correction, and the hope that we had is that it could be a large enough correction to account for dark energy, but it doesn't seem like it is. But it should be there at some level, and I don't know what the level is.
Yes. Could you tell something more about the sigma 8 tension? How many sigmas of discrepancy do you have there?
Yeah, I just have one slide on it because I anticipated that I wouldn't, there's only so many tensions and crises I can talk about. So there's this parameter sigma 8 that measures the amplitude of matter fluctuations in the late universe on a scale of 8, h to the minus 1 megaparsec. Little h is Hubble's constant in units of 100 kilometers per second per megaparsec. So we can determine this by CMB measurements and local weak gravitational lensing measurements. This is some results from a previous DESI, dark energy spectroscopic instrument results from last year, or maybe from last year. And this doesn't, so this is the Planck result from CMB in green. This is the dark energy survey in gray, and their measurements are over here. And there's a slight tension here. These are the various error, 1 and 2, 68 and 95% confidence limits. And so sigma 8 here, this is CMB, and these are the other 3 ways to measure that. Perhaps there's a tension here. That's the sigma 8 tension.
Thank you.
So I described this as a sigma 8 tension. The Hubble tension I described as the Hubble hypertension because it gets a lot more attention.
Okay, so, sorry.
So first of all, I think that there is, healthy is a strong word if there is really a 4.2 sigma tension with the W equal to -1. But I think that my question, so I have 2 questions. One is, which which data were used for the 4.2 versus like using BAO and CMB data? Like when you say 4.2, can you lower this tension by using more data? Like I remember that
this paper came out yesterday. I haven't really gone through it very much.
If that's true, that's pretty broken, I would say, lambda CDM, no?
I'm sorry, it's in, right, let me see if I can find it. Right, so this is the data, I didn't put the reference here, I meant to. It just appeared on the archives today.
Okay.
And so it's 4.2 sigma. And they're very, you know, in this game, people do one experiment and combine it with another experiment and do some meta-analysis. And I forget where the 4.2 sigma enters which analysis they combine, but that is what they're sticking with, that is disfavored at 4.2 sigma. And again, it just came out today.
The other thing was like at some point you talked also about the 3.5 kV line, but I thought that this was gone. Like there is.
Yeah, I think it's gone too.
Okay.
You know the.
No slide.
The signal disappears, but the people who propose it never disappear.
Ah. Thank you.
Okay, so if there are no other questions, let me thank again Professor Kolb for this grateful colloquium.